question. And let me see if I can easily land on, I take it it's in reference to a test question, is that right?
Yes, sir.
Okay, and which test question is it?
Just how to calculate initial velocity. I was trying to go through it.
As in number 2 on your test?
Yes, sir.
Okay, the initial velocity is given to you, right?
Calculate how the ball goes.
Okay, right. Okay, got it. Okay. I thought that might be what you meant, but that sort of threw me when you said initial velocity. I thought maybe I had typed the question badly. Okay, so let me turn back, and this will be in chapter 5, of course. And I believe that's probably 5.1 or 5.2. Let me see. No, 5.1, I'm pretty sure. If you go to page 290, do you have your book?
I have the online book. It don't
Online
tell me
book.
what. Yeah, yeah. It don't tell me what page.
Pages. Okay. It's in section 5.1, and um, okay, a sample like it would be example 9, which is the very last example in the section. And it doesn't actually ask how high the ball will go, but the function that you're dealing with there is, yeah, gives find the function, the position function, giving the height s as a function of time. And let's see if I can remember the question. I just had it in front of me and now I've moved it away. Hold on just a minute. And I think this problem is very similar to that one. And okay, let's see. All right, you actually don't need the entire, well, yeah, what you have here, eh, do you have the problem in front of you now or not? I mean the example 9, or you can't look at that, you can't look at, huh?
Oh yes, I found it right
Found
here.
it.
State example 9. Yes, sir.
Okay. Um, is that going to give you enough information?
Oh yeah.
Okay, you got it from there. I was going to say if that didn't, um, I believe in the questions in the um, thing in rectilinear motion on page, well, you don't have the page number in the homework exercises, or the whatever they call them, 5.1 exercises. Um, the number, well, I can't see but I think you'll find in that group that's between number 65 and 72, you'll find several problems like that. Um, and uh, is that going to be enough for you to go on, you think?
Yes, sir.
Okay, all right, okay, surely, okay. Good question, by the way, excellent question. Still no word from um, Jordan, huh? Okay. All right. We are recording. I got that done. Just trying to get my act together here. Let's start the share session with 7.1, and there it is. That's where we're beginning. Any other questions before we get started in 7, where we left off in 7.1? Any other questions? Excellent question, by the way. Let me also get this taskbar. Such a pain in the neck. It blocks right in the middle of the screen. Not in the middle, but close to it. Blocks a lot of the writing of the screen. So let me get that scooted over as far as I can there, and also get us moved over there. All right. And what you see here is example 2. We've already finished that long time passing, but this is where we pick up from the slide because they didn't have example 3, 4, or 5, and that's what we're doing is example 5. So we're going to need to go to the whiteboard to pick up there. Now I've got to move these things around. Its toolbar is of course in the way, and the whiteboard itself is behind some other materials, so I got to move it. I have so much open at once that, okay, I went too far. I know you just see a whiteboard and say, what is he moving? But on my screen, it is just a portion. All right, and let me get my pad ready. Now, I think I'm going to need to get, oh, one thing I forgot to do is turn on the overhead light. I was wondering why it was so dark in here. Hold on just a minute. Let me see if I can get the light on from where I sit. There we go. Sheds a little light on the subject, not too much. All right, any other questions before we get going on example 5? Okay. Now, this was mentioned, at the bottom of the previous page. What happens if your function is a function of y and you have delta y's as your intervals? And that's what example 5 is going to do. So it says find the area. Now in this one, remember, chapter 7 is applications of integration, and 7.1 is area of a region between two curves. Well, so far we haven't done, but well, yes we are. We're between two curves now. So let's get this one. Here's the first curve. If I can get my pen to show up here. Come on, pen, where are you? Okay, this is not good news, folks. My Wacom does not seem to be working, and I don't know why. Okay, maybe, the button got turned off. Okay, now let's see if we can get it to work. Yes, okay, sorry about that. Find the area of the region bounded by the graphs of, here's the first graph, x is equal to, will not write equal signs well, 3 minus y squared, and the second function is x is equal to y plus 1. Now, one way you could approach this is drawing graphs, and then by trying to get the graphs drawn properly, estimate where your endpoints are, where the points of intersection. That depends on estimation, which is not very precise. The better way, and it's basically in my mind easier, we want the 2 points of intersection, so we set these two equal to each other. Okay, this equal to that. For the same x, what are your y's? So we say 3 minus y squared is equal to y plus 1. What would you suggest we do now? Okay, These are quadratic functions, and with a quadratic or any higher order than 2 or higher, you want everything on one side, 0 on the other side. Sorry. Had a tough weekend with pollen and everything, so my voice is kind of breaking up some. So let's add y squared to both sides, because I don't like that minus there. So let's add it to both sides and get it over here. That's y squared here. And since we're moving things to the right, let's go and subtract the 3 here to get that over here on the right as well. Now I'm going to switch sides. Okay, I feel like a politician here. Here everything goes to 0, that goes to 0, this goes to 0. But I'm going to flip sides and have the y squared here plus y, and now it's a minus 2, plus 1 minus 3 is minus 2, set that equal to 0. Well, what do we do here? If y'all remember the F word, factor if at all possible. Okay, let's see if we can. Only possible factorization for y squared would be y times y. And then we look at the sign of the last term as a minus. That means these two signs have to be different from each other. Then we want two numbers that multiply to be 2, and their difference is 1, because these are different signs, their difference is 1. Well, that's obviously 2 and 1. Well, who's going to win the prize here? The plus is. So put the 2 with the plus and the minus with the 1. If you don't get it right the first time, try the second time. This is called trial and error. Let's check it and see if we got it right. When we FOIL this, we have y times y is y squared. That works. Minus y plus 2y, that would be plus y, and minus 2, yes, it works. So this gives us these two linear equations. Either y plus 1 is equal to 0, because anytime you have two entities multiplying together to be 0, that's why we want a 0 on the other side, one or the other of those has got to be 0. So either that's 0 or y minus 1 is equal to 0. Well, to get this to be true, subtract 1 from both sides, and that gives you y is equal to minus 1, or add 1 to both sides. That's a 2 there. I don't know how it became a 1. Sorry, I'm going too fast. Add 1 to both sides, and that gives you y is equal to 1. So those are the limits on your y. All right. Next thing we need to know is who's on, if this were x's, it'd be who's on top. What we want to know who's now is who's on the right, okay? Who's on the right hand side, who's on the left hand side, because that's going to be the difference, the height of your rectangles. However this is going to be, and I'm not going to draw an accurate picture here, but I'm going to draw. This is a parabola opening something like this. This is a line doing something like this, and here is the plus 1 up here, the minus 2 down here. So it looks like to me, the way I've drawn it, the parabola is to the right and the line is to the left. Let's see that. Again, that's a guess. Let's not guess. Let's pick a y in between minus 2 and 1. Easiest one for me to be 0. And up here, if you put y is equal to 0, you get x equal 3. Here you put y is equal to 0, you get x equal 1. Sure enough, the quadratic, the parabola, is to the right. 3 is greater than 1, so therefore we're going to do our subtraction that way. So the area then will be, and that's what that's what we're looking for. And by the way, without drawing the axes in here, wherever they are, we're doing dy's. Okay? So that's our rectangle. Here is this value is your maximum value to the right. this is the minimum value to the left down here. Okay, this is the maximum to the right, and there's the minimum to the left. So the difference of those two is the length of that rectangle. The width of the rectangle, of course, is dy. Okay, and we're integrating from minus 2 down here, y is equal to minus 2, to y is equal to plus 1 up here. Now this is without a graph at all, but just the general idea of where it's going. And you're looking at y values. These are y values, this is a dy, this should all be in terms of y, which is what we've got here. So the area will be the integral from minus 2 to 1 of the far to the right, that's 3 minus y squared, minus the 1 to the left, that's a y plus 1. If it's all right with you, I'm going to go and write it as minus y minus 1, because the minus would go in front of the whole thing, and it would be an extra step to do, and that's your length is there, your width is your dy. And that should be the entire area. Okay, we got a little bit of cleaning up to do, not too much. This is the area, would be the integral from negative 2 to 1. Now, do you care which way if your integrand is in descending order of the powers, whichever comes first? Do you care? How would you simplify this integrand here? There's only one simplification to do. 3 minus 1 is 2. It's just whether you want to lead off with 2, you want to leave off with a minus y squared. What do you want to do? You tell me. Okay, let's start with the minus y squared. Minus y squared minus y, I take it you want it in descending order of the powers, and then that will be a plus 2. 3 minus 1 is plus 2, and that's what we're integrating dy. Okay, now the area will be, let's go on and do the antiderivative. What's the antiderivative of minus y squared? Power rule, right? Increase the 2 by 1 and make it a 3, and divide by that 3. Remember? Next term, antiderivative of minus y. Increase the power by 1. It was a 1, increased by 1, that's a 2. Divide by the 2, right? Then the plus 2, I don't see a y there. Of course you don't. So that's y to the 0th, add it to 1, add 1 to 0, you get y to the 1st. We don't have to write that down. Divide by 1, we don't have to write that down. And evaluate this from minus 2 to 1. Okay, the rest is algebra. A little messy, but still good. Here it'll be a minus 1/3, plugging in the upper limit, minus 1/2 plus 2. When you put y in for 1 in for y. Now, we need to subtract when we're doing the minus 2. Well, a minus is going to be a plus, but then when you put a minus 2 and cube it, that will be a minus 8. So that plus goes back to being a minus, so that's a minus 8/3. It seems like we did this problem. Did we? It seems so familiar. Maybe we did it in another lifetime. Okay, so that's the first minus 2. Okay, that's where you plug minus 2 in here. Then we've got a minus, which becomes a plus this time, because when you square minus 2, it becomes a 4. And 4 over 2 is 2. Okay, And then when you put a minus 2 in here, it's minus a plus, which will be a minus, but then you put a minus 2 times 4 times 2 is a plus 4, because minus is plus. Watch out for those minus signs. Their only function in life is to trip you up. Okay? I thought for sure we have done this one before. Here we have a total positive of 4, and 2 and 2 is another 4. That's 8. So that's a plus 8. Okay? And here we have a minus 1/3 and a minus 8/3. That's minus 9/3. That's a minus 3. And then you have a minus 1/2. Okay? So this would be a 5 minus 1/2 would be a 4.5. And change that to an improper fraction, which I think is what the book will do, and I get 9/2. Now, I don't know if that seems right or not, sort of hard to tell. I'll look at the book, and yes, sure enough, that is correct. Okay. Now, I know some of you can't have your books open and Zoom open at the same time, so I'm going to show you the pictures here. My picture there, this is what they did on an actual graph. And you see we're not too far off, okay? I didn't draw the axes in there, but they did. And there is what the picture looks like. There's your representative rectangle, okay? The thickness of the rectangle is a dy. The length is from the parabola back to the straight line. Now, they said, what if you had done the dx's? Look how bad that would have been. To the right of that point 1, 2, is that point? I can't read it upside down. 2, 1, 2, 1. I'm reading it backwards. To the right of 2, 1, where is it? I had it, there it is. To the right of that, you have to go going from the lower lobe of the parabola to the upper lobe of the parabola, okay? But then, once you hit that point there, you're going from the lower lobe of the parabola, or just the parabola, up to the straight line. So you have to break the function into two pieces, add the two integrals together. What a pain in the neck. So even though we're not used to doing dy's, in this case, that's the way to go, folks. That is definitely the way to go. Now they show you at the bottom of the page there, and I'll hold this up a little bit longer. It's a heavy book. There is where you do the integral of the dx's, the one that you're showing there. The first integral is from, I can't even read here, but if you can see that, integral from the upper, well, no, I can't read it. I'm going to have to set it down. The first one they showed is from the left, from the line down to the integral, because the line was on top. But you have to change everything here, right here, and make y is equal to x minus 1 to solve for y. Here, that's even worse. This is y squared is equal to 3 minus x. Then you have to take a square root, and it's plus or minus the square root of 3 minus x. That's what y is. So when you're going here, that's going from x minus 1 down to the negative square root. So you're subtracting a negative is adding, okay? So you're doing that square root. Then when you get here, you do the plus square root minus the minus square root. And that's a pain in the neck. And they show how you do that and what your integrals look like, how much more work it is, not just to do the integration, that's more work, but to set it up to do the integration, that's even more work. And you still come up with the right answer as long as you don't make any errors in that. Many more potential areas for pitfalls there. So be careful. Use your dy's if that makes the most sense. All right, any questions on that? I know that was sort of me doing too much talking, but it was kind of a tough problem to get a lot of feedback on. Any questions on example 5? Okay. If not, let me just check and make sure. Nope, still got 3 people. Ashton's not, I keep forgetting his first name. Jordan is not here yet. Okay, so let's go back to, let me minimize that, and go back to the slideshow. And I'm pretty sure, nope, they moved around. I don't know why. Let's go back here. And there we go. And let's go from current slide. Okay. Everybody can see that slide, right? That was the end of example 2. We finished example 2 last week. Not going to do, yeah, that's where this one worked out being the same answer and a lot of the same problem as what we just had. Okay, it just happened to be, it was that this was dx's, that was dy's. I knew that looked awfully familiar. Okay, when you were plugging in. Okay, now we're doing integration as an accumulation process. This is on page 449. Again, chapter 7, application of integration, 7.1, the area between 2 curves. Now this is talking about integration as an accumulation process. And this does make sense. It is true. And I'm sure there's some application for it, but very seldom do I ever use this. The main place is understanding what they mean by the fundamental theorem of calculus part 2. This actually illustrates this pretty well. Okay, the integration formula for the area between 2 curves was developed by using rectangles as a representative element. For each new application of integration in the remaining sections of this chapter, which is not going to be too much, an appropriate representative element will be constructed using pre-calculus formulas you already know. Okay? Each integration formula will then be obtained by summing or accumulating the representative elements. So we'll start with known pre-calculus formula. Well, frankly, the area of a rectangle is a known pre-calculus formula, so we were already doing this. We'll then understand our representative element. Well, this was a simple rectangle. We'll be doing something else, and we'll be producing a new integration formula. They make it sound like it's all new stuff. It really is just a continuation of what we're doing. Let's see how it works. Here is, for example, not an example, but for an example. For example, the area formula in this section was developed as follows, and this is what we're just doing. The area was height times width, that's from pre-calculus algebra. The delta area would then be the length of that rectangle, representative rectangle. That's the upper to lower because this is functions of x, okay, same x's, and then the width would be your dx, delta x. Your area would be the, rather than a summation of the deltas, an integration of the d's, okay, and that's going from a to b, the left-hand endpoint of x to the right-hand endpoint of x, of every one of these representative rectangles, f of x minus g of x, that's the height times the width, dx. And basically we're accumulating as well. They're not saying that. Okay, so let's move on. Here's example 6. I don't know. I don't know why that little blurb was given there. There was nothing new in my mind in it. Find the area of the region bounded of the graph by y is equal to 4 minus x squared and the x-axis. And it says describe the integration as an accumulation process. Okay? Well, you have to know, well, at the x-axis, what is your y value? Anybody? On the x-axis, what's your y value? Zero, right? Y is 0 on the x-axis. It's neither up or down, it's 0. Okay? So, Your lower limit's going to be 0. Your upper limit is going to be this one. Well, let's see where this is equal to 0, and we'll find our points of intersection. Well, that's going to be pretty easy, I think. So let me get my pen and pad ready, and let's do this. So we just basically are saying, where is my pen? Whoa, get out of there. Okay. My pen is nowhere to be seen. I'm going to make a little mark and see if I can find it. Okay, does something shut off again? I don't know why the pen's not writing. I found the... Well, for some reason, this isn't writing now. Everything's turned on. Well, this is a mystery. Okay, I don't know why the pad's not working today. All it's doing is acting like a button for me. Did I hit some? Nope. Still no go. Okay, I have no idea why I can't write with my pad. It beats me. Okay, so I guess we'll have to go to the white pad and do it. In the past, I've been able to write, and it's always written in red. Remember? A thin red line. It's not doing it this morning. Okay, so let's go to the white page, whiteboard. I'm sure there's some reason for this. I just don't know what it is. I tell you before we go, I'm going to do this. I'm going to hit all the buttons on the pad and see if that does nothing. That does nothing. Except make a mess, okay? I don't know if y'all can see these things showing up now too. Okay. Okay. Let me try this button. Still nothing's happening. It just acts like a return. And folks, I have no idea what it's doing. So forget that. Sorry about wasting time trying to make it work. It's not going to work today. Okay. Will the whiteboard work? Okay. So let's clear this. Anyone need that any longer? Okay. So here we have y is equal to 4 minus x squared, right? Okay. And the x-axis. And rather than writing the x-axis, I'm going to write it this way. Y is equal to 0. That is the x-axis. What's the point of intersection between those? Set 4 minus x squared equal to 0. Add x squared to both sides. I don't like to deal with the minuses. And we'll subtract 4 from both sides too, because it is so this side becomes 0, and I'm going to switch sides now and make this x squared minus 4 is equal to 0. Now you probably had already figured this out. This is x plus 2 times x minus 2 equals 0, and that tells you either x is equal to minus 2 or x is equal to plus 2. Those are our two endpoints, x going from minus 2 to plus 2. Okay? Your length of the rectangles are from the top to the bottom, so it's from here to here, this minus that. Okay? And here we go. Here's the integral then. The area would be the integral of 4 minus x squared minus 0 dx, going from minus 2 to 2. Now time out. Notice this, why in the world, oh, I'm doing the wrong path. This is an even function. Exponent here is 0, exponent here is 2. Both of those are even numbers, so that's an even function. It's symmetric across the y-axis, going from minus 2 to plus 2, even function. Hey, all we have to do is go 0 to 2 and double it. So I'm going to rewrite this as the area is equal to twice the integral from 0 to 2 of the same thing, 4 minus x squared dx. Okay? Now, what's the antiderivative of 4? Anybody? 4x minus, what's the antiderivative of x squared? Anybody? Power rule, x cubed over 3. Just done that not long ago. Evaluated from 0 to 2, but doubling that. Okay, so this will be 2 times, plugging in the 2 here gives you 8, minus, plugging in the 2 there is 8 thirds, and plugging in the 0 you get nothing. Okay, so this will be, that's one reason I like to do this. If you can do it, make it simpler on yourself. Plug in 0 is much easier than plugging in minus 2. Remember, those minus signs are there to trip you up, so don't let it happen. So this is 2 times. Now, you can do this any way you want to. 8 thirds is the same as 2 and 2 thirds. If you subtract that from 8, if you subtract a 2 from 8, you get 6, but then subtract another 2 thirds from it, you get 5 and a third. So you could write that as 5 and a third. But if you don't like to do that, you could have changed this to improper fraction. This would have been 24 thirds minus 8 thirds would be 16 thirds, which is exactly what you get here. So 2 times 16 thirds would be 32 thirds. And that's what we've got as a solution. Now, what they mean by an accumulation process is drawing a graph, which is always a lot of fun. I didn't want to do. And what they're talking about here, and it's basically doing what we did. Now, remember, we cheated. We took the easy route and just did 0 to 2, but you can do the same accumulation process here. There was the original from -2 to -2. You don't get anything. Move it a little ways, I think that's -2 to 1, and you've got that much of the area. Move it to -2 to 0, you get that much area. I would have stopped right there and doubled it and gotten the answer, but they took it on another step and moved it to 1 and added that to it and then did all the way here. Why would you want to take that many steps to do something that was this simple to do? I don't know, but that's indeed what you're doing. You're accumulating as you go from the left endpoint, -2, to the right endpoint. That's what you're doing. You're accumulating the area as you go, which is the same thing we've always done. Okay, so what's the big deal? And they do nothing more with it. Okay, that's it. Let me make sure that's the last slide. Oh wait, let's see how they do it. I'm sorry. So let's go back to the book, and that way you'll see it. I'm sorry I wouldn't have held up the book then. Go back to the book here, and current slide here, and The area is just what we had before, the integral from minus 2 to 2, 4 minus x squared dx. Exactly what we had. They didn't show you how they got the minus 2 to 2. They just assumed you could do it out of the blue sky, you know, but we did it. Pretty easy. Okay, now, they're not going to make it simpler only by doubling from 2 to 0 to 2. We did that. They didn't. But that's okay. You can think of the integration as accumulation of the areas of the rectangles from left to right as you go from negative 2 to positive 2, as shown here, and this is what I was trying to show you. When it's negative 2 to negative 2, of course, you're starting right here. Yuck! Starting right here, and you have nothing to integrate. And then when you collect all those rectangles up to negative 1, you go to that part, and that's 5/3. Why do this integration over and over again? I don't know. And then you accumulate as you go from negative 2 to 0. I would have said from negative 1 to negative 1 to 0, then add that to that, but no, sure this is right, but why in the world would you do the integration, the same integration, 1, 2, 3, 4 times, rather than just plugging it in once, or splitting it and doubling it and doing it once, and even a simpler thing? I don't know. They're trying to make a point, but it's a really lousy point. I mean, what's the deal with it? I don't know. All right, but anyway, that is the last slide in the section. So, homework exercises here. Now again, I don't usually say much about the concept check. A great thing for you to look at, read that, make sure you can answer that question. What is a geometric interpretation? Blah, 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 blah. Describe this. That's good review for you. Make sure you understand what they're asking for, then start doing the exercises. So do any of the odds, 5 through 9. They're all at Calc Chat. 7's at Calc View. 11 or 13, both at Calc Chat. 11's at Calc View. Any of the odds 15 to 27, they're all at Calc Chat. 17's at Calc View. 29 is both at Calc Chat and Calc View. 31 to 35 are all at Calc Chat. They say you may need a graphing utility to do it. I don't think you need one, but if you got it, use it. If you can't get it otherwise. 37 to 41, they're all at Calc Chat. The odds are 37's at Calc View. 43 or 45, again, they say they might need a graphing utility. They're both at Calc Chat. 47 or 49, they say you may need a graphing utility. They're both at Calc Chat. I don't think you'll need one, but you might. Then 51 is at Calc Chat, and either 53 or 55 is at Calc Chat, with 53 being at Calc View. 57 or 59 are both at Calc Chat. 61 and 63 are both at Calc Chat. You can explore doing 65 or 67 if you're interested. Okay. 69, and they should both be at Calc Chat. 69 should be at Calc Chat. 71 should be at Calc Chat. 73 should be at Calc Chat. 75 should be at Calc Chat. And then the odds 77 through 85 should all be at Calc Chat. But time out just a moment here. 77 is talking about a Lorentz curve. Okay? That's a good thing to look at to say, hey, who in the world was Lorentz? Is there a reason that name's in here? How does he develop? How did he develop this curve, the Lorentz curve? And you might notice these are economists that are using this, not engineers and others. So if you're into economics, what is the model they're using it for? How is it used? That kind of stuff. So you see several potential paper topics just in that one example. Okay. Oh, I'm sorry. I sort of mixed two things together. I'd say odds. Where did I start that? 77. I should have stopped you at 81 and said any of those are at Calc Chat. 83 and 85 are true false, and they're also at Calc Chat. So, all right. Any questions? 7-1. All right. First application of integration, area. Area between two curves, whether the curve's the x-axis or a separate curve. Area between two curves, very practical application of integration. Okay, the next one, that's not really what I wanted to do. Let's get out of this. Well, I think I'll just close it. Okay. I couldn't write, that must be why it was. So let's go to a new share and we'll go to 7.2. And there's 7.2. All right. Now, unfortunately, I've got the same stuff to do over again. Let's get the slideshow set up for current slide. And why is, oh, I think that's old news there. You can see my slide, can't you? It says it's showing, but the other thing said you weren't showing, but I think it is. So chapter 7, application of integration. Here's the second application. If I could get the slide to advance. I have to click on the screen to get the slide to advance. Okay, there we go. Volume. Okay, we're going to look at two different ways to calculate volume. Now this is a volume of a curve going around an axis. Some curve going around some axis. Okay? The first one we're going to look at is called the disk method. Okay? And they go into a lot of gory detail here. It turns out being, I think, simpler than what they make it out, but let's go with it. Okay? Our objectives here are to find the volume of a solid of revolution using the disk method. We'll find the volume of a solid of revolution using the washer method, which sounds like a new method. It's really pretty similar to the disk. Okay? And then we'll find the volume of solid revolution of known cross-sections, and we'll do that one. Okay? So, let's start with what in the world do we mean by the disk method? All right. When a region in the plane, a flat sheet, okay, is revolved about a line this way or this way, the resulting solid is called the solid of revolution. So all these are going to be symmetric about some axis, okay, vertical axis or horizontal axis. The line is called the axis of revolution. That's what you're revolving around. The simplest such solid is just a right circular cylinder or a disk. Okay? So let's just imagine you had a line right here. There's a horizontal line, okay? Y is equal to 7, 3, or whatever that height is, that R that they're showing here is. And you're taking that line, and that line has some width to it, they're calling W, and you revolve that line around, say, the axis of revolution. That could be the x-axis, it could be y is equal to 7 or y is equal to -3 or anything like that, okay, to give you that as your radius. Revolving this line around that axis, you form a disk. Now they turned it to the side so you can see, make sure that, yep, make sure that you can sort of get the three-dimensional characteristic of it. You're taking this rectangle that we had right here, there it is, revolving it around that line. This end of the disk stays side, that's your pivot point. Your rectangle goes all the way around, you form this disk. What's the volume of the disk? It's the area of that disk, which is pi times r squared. That's the area of the disk times the thickness of the disk, W. So the volume of that disk would be pi r squared times W. Okay? That's it. That's a simple horizontal line revolved around an axis of revolution. Whatever this r is, now part of our problem is going to be calculating what that r is, what that radius is. Okay? Not a hard thing to do. In the future, this W is going to be our delta X, or if you put the axis the other way, delta Y, okay? Whichever way you orient it, okay? And then you're going to be revolving. So here's what they're going to. The volume of such a disk is the area of the disk, pi capital R squared, times the width of the disk or thickness of the disk, W, where R is the radius of the disk, excuse me, and W is the width of the disk. That's a simple disk. Horizontal line revolved around a parallel axis. Okay. Now, to see how that's used to see how to use the volume of a disk to find the volume of a solid of a general solid of revolution, consider a solid of revolution formed by revolving the plane region in 714, this right here, about this. Now here's your plane region. Here is your x equal a to b, and you're doing this curve. And we're just going to call that, I think, probably f of x. Sounds like a reasonable thing to call it to me. Well, and if you're using the x-axis here, or whatever your axis of revolution is, your r is the distance from, why is this happening? Oh, I've just lost Zoom. Sorry about that. You can't hear me. I'm going to stop my recording now because that's sure good for Alabama. Okay. And where were we? Right here. All right. And we got a new share, but now I've got to move this thing out of the way again. This is such a pain in the neck. They're so hard to move right here. Okay. Not hard to move, but just, now why is it disappearing here? I don't know, but that's fine with me for it to disappear as much as it wants. Okay, let me scoot y'all a little further to the right. Okay, so to see how to use the volume of a disk to find the volume of a general solid of revolution, consider solid of revolution formed by revolving this plane region. Let's just call this y is equal to f of x, this curve right here. Whatever curve that is, y is equal to f of x, around this axis down here. Okay? Now we're just going to look at one of those volumes, this little rectangle here. We're going to pick, let's say, the midpoint of that rectangle. That f of x at that point is going to be the height above the axis here. So it's going to be this height minus whatever that value is here. Y is equal to f of x minus y is equal whatever that is. That's your radius. Your thickness is going to be your delta x. Okay? Now, if you do that for this curve, if you picture rotating this curve around that axis down here, whatever axis that is here, you get basically what looks, I'm hungry, so that looks like a Hershey's Kiss with the top picked off, okay? If any of you are into Hershey's. Otherwise, you might think it's sort of like a Christmas tree stand. Whatever you think of that as, that's your shape. Well, this little rectangle here, revolved around that axis, is going to be that little disc right there. See, half of that thickness is sticking out, and half of it is sticking in. So there's the part that's sticking in, there's the part sticking out. That revolved around here is your disc, the volume of that disc. Not exactly the same as the volume of that, but it's not too bad. It overshoots here, undershoots here. Okay, you have this you're not accounting for here, this you're over accomplishing. It's going to be pretty close. Now do a whole bunch of those in disk from A to B, and you have something that looks like, I don't know, maybe a wedding cake or something like that. The layers are getting smaller and smaller, smaller. On the side, you can tell I'm hungry. Hershey's Kisses and wedding cakes, you know. That's where my mind is now. And the area of this, or the volume of this, would be pretty close to the volume of this one. How do we make it closer? make n larger, making the delta y or delta x smaller, and then do more of them, more layers on that thing until you get something that really does look like the disk. That's what we're going to do. So what is that? That's integration, right? The delta x's become the dx. You're going from a to b. Those are your limits on the integration. What is your rectangle here, the radius here? It's whatever the f of x is minus whatever the axis is here, okay? And that's it, okay? It won't advance now, okay? There we go. To determine the volume of that solid, consider a representative rectangle in the plane region. When that rectangle is revolved around the axis of revolution, it generates a representative disk whose volume is the delta V for just that little volume there of thickness delta x is pi r squared. That r is the radius of that the length of that rectangle that's going to be going around there. There is your r, capital R, that's the length, f of x minus whatever your axis of revolution is. That's what that is, and then your delta x is your thickness of that element. Approximating the volume of a solid by n such disk of thickness delta x with radius r of x sub I, where x sub I is some value in that between, I minus 1 and I, some value in there, and the radius is some function of that. Then the volume of revolution would be the summation of all those n rectangles, 1 to n, of pi times that r of x sub I squared times your delta x. Well, the pi is a constant. It can come outside, and you're left with the summation from I is equal to 1 to n of r of I, r sub x sub I squared times delta x. Okay? Now, that approximation appears to become better and better and better as you get smaller and smaller and smaller delta x's, as your n is going to infinity. Then your norm for all those subdivision, the largest of those delta x's, that's your norm. So as that norm approaches 0, as x goes to positive infinity, you can then define the volume as being the limit as that norm goes to 0, which is n going to infinity, pi I equal 1 to a very, 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 very big number, r of x sub I squared, the radius squared, times the delta x. Well, this is a hard thing to do because you have a lot of summations here. So pull the pi on the outside and take the limit of the summation to be the integral. And now you're going from the lower limit x, a, to the upper limit b, and you're doing the radius squared, whatever that function is, squared times your dx. Excuse me just a moment. My voice is going on me again. I meant to bring up some carbonated drink because that helps keep it a little looser, but I was in a hurry and forgot to bring it up. So schematically, the disk method looks like this. Your known precalculus formula, that's the volume of a disk, pi r squared times w, okay? Representative element, the delta V of one of those little bitty disks, pi times the, get out of there, okay, capital R of x sub I squared. And a lot of our problem in the future is going to be calculating that, what that length is. Usually a difference between your upper curve and your axis, okay? And then your delta x is just delta x, and that's it. So the solid of revolution would then be integrating this, and it becomes v is equal to pi times the integral from a to b of the r of x squared dx. Okay. Pi r squared times the height. Okay. Similar formula can be derived when the axis is vertical as opposed to horizontal. Excuse me. So to find the volume of a solid revolution with the disk method, use one of these formulas. The horizontal would be volume is equal to V is equal to pi times the integral of r of x squared dx. Pi r squared is the area times dx is the thickness. Okay. Or the vertical axis is V is equal to pi times r as a function of y squared, okay, times dy, okay. And that would be going from C to D, where C to D are your limits on y, A to B are your limits on x. So this would be, if this was going around the x-axis, well, not the x-axis, a horizontal axis of revolution, this would be, the volume be pi times the integral from A to B, okay, of whatever this radius is. That would be the functional value up here minus the axis value down here. That would be the length, radius, squared times your delta x. Or if you're going around, around the y-axis here, then your volume will be pi times your integral from you'd have to convert this to y as a x as a function of y here, and whatever that function of y is minus whatever the value for your vertical axis of revolution, that would be your r that you then square, and now you're going from C to D here. You square that r of y, and then you multiply that by dy, where up here it was a delta y. Well, on the previous slide it was a delta y. And that gives you your volume of revolution. Whew, solid of revolution. Here's the other thing, folks. We had to get up from Georgia this morning at about, it was 4:45 Georgia time, which was 4:45 this time. So that's how long I've already been up today, and I am beginning to lose a little coherence here. So if I start mumbling too much, yell at me or something, okay? So there's your formulas for the disk method. Here's example 1. To find the volume of a solid formed by revolving the region bounded by the graph of f of x equal to square root of sine x and the x-axis, and you're going from 0, x going from 0 to pi. That's a very good range to go, because sine of 0 is 0, sine of pi is 0, and it's positive everywhere in between. So basically it's one loop, positive loop of your sine curve. Half of a sine curve from 0 to pi. The other half goes negative. We don't want that. We want the positive part, 0 to pi. That's your, and you were doing the square root of that to boot, okay? But you know that it crosses the x-axis at 0 and at pi, because sine crosses at 0 and pi, and the square root of 0 is 0 for both of those, okay? So, they don't tell you, but it says, oh yeah, there they say, about the x-axis. So our radius is only going to be the r value, the f value, because your bottom limit here, the axis of revolution, is y is equal to 0. So you're going from y is equal to square root of sine x, that's the upper part, to y is equal to 0 down here. So it's square root of sine x minus 0, which is just square root of sine x. That's your upper limit, okay? That's your length of that rectangle. The thickness is delta x, and that radius there is what you're going to square. So you got pi times this thing squared times the dx from 0 to pi. So it looks pretty straightforward. here you have it. They made it look a lot like a football here, doesn't it? Okay. Certainly good for the southeast here to have footballs in the problem. All right. Now I'm going to try it again, even though I know it's not going to work, or I don't think it's going to work. I don't know why it won't work. Let's see if, hey, look at that. Now it's working. I don't know what happened between before and now, but I've got my pen back. That's good. So what we have is the volume is going to be pi times the integral from 0 to pi, that's the x value, 0, x equals 0 to x equals pi, of this f, that's your radius here because it's that minus 0, that's the square root of sine x, squared. When you square the square root of sine x, you just get sine x. And then the thickness of that interval is dx. This delta x becomes a dx. So this is going to be pi times, oh, let's go on and do the antiderivative. What's the antiderivative of sine? Anybody? It is negative cosine because the derivative of cosine is negative sine, so the antiderivative of sine is negative cosine. And this is going from 0 to pi. And why in the world I put a pi there, I don't know. That's an, hey, I forgot this. I hadn't even thought of that. I can erase on this slide. I don't know why I did that instinctively, but I did. This is just like the old days. Okay, all this time I've been saying I can't erase on this slide. I just came down there and did it. It's just like the old. Hey, thank you, Brandon. Okay. If y'all remember, if any of you were in my class when we had integrity, that's how it worked. And I just did a flashback in my haze of not enough sleep. I went back and did that, and it worked. Amazing. All right, so let's go from here. So what will this volume be? It's going to be pi times minus cosine of pi. Can anyone tell me what cosine of pi is? Cosine of pi. Pi starts at 1, goes down to 0 at pi halves, and down to -1 at pi. So that's a -1. So it's a minus 1, which is plus 1, minus a minus, which is plus the cosine of 0. And what is cosine of 0? One. Okay, it's 1. Goodness gracious. Okay. So what does this give you? 2 pi. That's the volume of that football right there that they got from integrating the square root of sine x from 0 to pi. Excuse me, square root of sine x squared from 0 to pi. All right, let's see if we can find where they are there. Oh, this is, I didn't flip the page. Page 456, top of the page, example 1, 2 pi. Good deal there. Okay, now, y'all are going to have to help me with time today because my watch is still on Eastern time and I have 12:22, so I'm taking that means we're on 11:22, or is my watch totally screwed up? Is it 11:22?
Yes, sir.
Good. Okay. Okay. So we will just remind me at 11:40 we stop. Okay. I might get carried away here. So let's see how they do it. So let me see if I can figure out a way down here. Since I discovered this down there, I mean, this is just amazing. Erase all the ink on the slide. There it goes, and it's gone. Another hand, Brandon? Okay, never mind. Okay. All right. From the representative rectangle here, right here, this one right here, the height of this is square root of sine x. Okay. And that's your radius. Okay, that's what you're going to revolve because you're going around the x-axis. So that height is your radius. You see that the radius is the f of x, and that is square root of sine x, but we're going to square that because it's pi r squared times your delta x, so that's going to be pi on the outside, the integral, excuse me, losing my voice again. Oh man, it was a beautiful, wonderful weekend, but the grass, when Sally went through, I don't know if you remember, we got a quarter of an inch of rain here. They got in excess of 5 inches of rain on the farm. So the grass was just amazingly tall and thick. My older brother, had bush hogged it on Friday a week ago. Sally went through on Wednesday night and Thursday morning over there, dumped more than 5 inches of rain. My older brother went in with a bush hog on Friday. It finally had dried up enough he could get in there, mowed it, but then all that moisture in the ground, the grass was growing right back through the thatch that he had mowed. So I had to get him a little Gravely tractor and mow it again, and then we had to mow. So I was just out there all Friday afternoon, almost all day Saturday, and just not really too much. No, in fact, none Sunday morning. We got it all done Saturday, just barely before it got dark, and I'm just so clogged up from all that. I got rained on, all sorts of things. So sorry about my throat. All right, so there's the volume. Okay, the radius squared, but the radius was the square root of sine x. The radius squared is the square root of sine x squared, and that would then be pi times the integral from 0 to pi of sine x dx. And just like I believe it was Ashton said, that is pi times the square root, the minus cosine x from pi to 0, 0 to pi. And at pi, that's a minus 1, which is minus a minus, which is plus 1. Then minus a minus cosine, so minus and minus again is plus. Cosine of 0 is plus 1, and that gave us our 2 pi. Because 1 plus 1 is 2. Didn't know you'd be doing such high-level math today, did you? Okay. Any questions on that one? Very nice of them to give us a simple square root of sine x. Looked like a weird function to give us because they knew we were going to square it. Came out something nicely integrable. Okay. Now, they're skipping example 2 before they get to the washer methods. So let's go to example 2. Go back to our whiteboard. All right. And now I have to move everything around again. I think this is because we went to a new section in the book. So let me move this around too. I know y'all don't think I'm moving anything, but really I am. Oops, moved it too far. Move it north as far as I can. All right, that's about as best I can do. So here's example 2. Find the volume of the solid formed by revolving the region bounded by the graphs of f of x is equal to 2 minus x squared and g of x, which is equal to 1. Okay, about the line, y is equal to 1. Okay, as shown in the figure. Well, thank you very much for having the figure here in the book but not doing a PowerPoint of it. That really makes my day. Okay. I guess it's most instructive if I try to draw that axis. Okay. So here's my y-axis. Let's just imagine that's a straight line. I don't know where to put the x-axis. I'm tending to put it down here. Okay. And let's tick off a few points. 1, 2, 3, 4, 5, 6. 1, 2, 3, 3, negative 1, 2, 3, negative 1, 2. Okay. Pretty ugly axes, but just to see what we can do. F of x is equal to 2 minus x squared. Okay. I'm so sorry. This long day is getting to me. On top of everything else, my home in Georgia, or our place in Georgia, both of my brothers and my sister all live on the farm in Georgia. Okay, we're the only ones that live outside the country in Alabama. Okay, so foreign government here. So when we go over, they all have to come by and see us. And we had rain yesterday afternoon, so I thought, hey, I'm going to get some grading done. I'll just relax a little bit. We had gotten just about everything done we needed to do by yesterday morning. It started raining in the afternoon. Well, sure enough, my younger brother came by. Thank goodness he came by and helped a little bit. So he helped, and we got done before the rain got too heavy. And then we had lunch pretty late, but we had lunch. And then I can't remember the order. I think he came back and left again. And then my sister came over and she stayed. And then she left. And just about the time she got gone, my younger brother came back again. And he stayed, and he wanted to talk with my older brother, knowing he was going to show up sometime. So he stayed until my older brother showed up, and then he showed up, and then my younger brother left to go eat supper, and my older brother stayed until after 9 o'clock last night, which was 10 o'clock. Well, no. That was 9 o'clock this time, 10 o'clock their time, and I had to get up at 4:45 their time, so 4:45 our time. It was not a pretty thing, but anyway, it happened. So let's go. I'm so tired. Sorry about all the excuses here. So here's what we've got. Now let's just figure out where we are here. Let's do the F first. When F is equal to 0, when x is equal to 0, F is equal to 2. So 0, 2 is right here. Okay? Now, when x is equal to 1, this will be 2 minus 1 squared is 1. So that's 1, 1, and negative 1, 1. Because when x is equal to negative 1, 2 minus 1 is still 1. Okay? And then when x is equal to the square root of 2 plus or minus, that's about 1.4, that's when you're down here. Okay, so this is a parabola that does something like this. Okay, something like that. But the axis here, where g of x is equal to 1, g of x is equal to 1, that's that line right there. This is F, and this is G. G of x is equal to 1. Okay? And that's also going to be where y is equal to 1. That's your axis of revolution. So revolving around that. So what's our disk here? Let's just draw a representative. There's your dx. And it's going to be this function minus 1. that's your axis, that's your radius here. It's f of x minus g of x. That's your radius, because that's what you're revolving around, and that's going to be 2 minus x squared, that is so ugly writing, minus 1, which of course is 1 minus x squared. Okay, so there's our radius. Your volume is going to be pi times the integral. And where's your integral going from? Minus 1 to 1, because you're just going to those points there. This is the only part getting revolved. Nothing out here. About that line, okay? So you're going from minus 1 to 1. But guess what, folks? This is symmetric about the y-axis, and you got a symmetric interval here. So let's just double that, put the 2 in front here, and go from 0 to 1. Okay? And what's your radius? 1 minus x squared. And, oh wait, that's your radius squared dx. Okay? So that's even going to be more symmetric. I mean, just, it's still symmetric because you're squaring that. Your radius, this is your radius. And you want the radius squared, so you want this thing squared. Okay? So let's actually square that. This will be 2 pi. This isn't the only way you could do this, but to me it makes more sense this way. The 2, because we're doubling from minus 1 to 1, we're doing 0 to 1. And this will be 1 minus 2x squared plus x to the 4th. I'm squaring that binomial. Square the first, twice the product of the 2, square the second. And this times dx. Goodness, I'm tired. 2 pi times antiderivative of 1, anybody? X. Antiderivative of minus 2x squared minus 2x cubed over 3. Power rule. Plus x to the 5th over 5. Evaluate that from 0 to 1. Thank you very much. Okay, that will be 2 pi. Goodness gracious, I'm tired. This will just be 1. This will be a minus 2/3, because when you plug in a 1, you get that. And this will be plus 1/5. Now that's a lot of fractions, and then the zeros will give you nothing. Okay? Now I think on this one we're going to have to go to least common denominator. Least common denominator is 15. So what we'll have, if I can find my pen again, here it is. So this will be a 2 pi on the outside, and 1 will be 15 fifteenths. Everybody agree that's 1, right? Minus, if you multiply that 3 times 5, you get 15 down here. Multiply the minus 2 times 5, you get minus 10. Okay? Multiply the denominator, 5, by 3, you get 15. So multiply the numerator by 3, and you get 3. So the reason I wrote 5. So 3. Okay? Now what does that give us? 18 fifteenths minus, I don't know where that minus came from. That's just a 10. Okay? I think I did the minus here and then put a minus up there too. So that's just minus 10. So 18 minus 10 is 8 fifteenths. Double that, and you get 16/15 pi. Let's see what they got for their, oh my goodness gracious, they got 16/15 pi 2 also. All right, we've got 2 minutes. Okay, do you think we can do anything on the washer method in 2 minutes? I kind of think not. So what I'm going to do, if I can find it, and unfortunately I didn't get it out of my book bag. Hold on just a minute, I'll be right back. Alright, sorry. We'll be starting with the washer method on whatever day the next one is, Wednesday. Told you I'm sleep deprived. Homework exercises here would include any of the odd 5 through 7. They're both at Calc Chat. 5's at Calc View. Okay. And I think you can do either 9 or 11. They're both at Calc Chat. 9's at Calc View. Okay. I think you can do either 13 or 15. They're both at Calc Chat. 13's at Calc View. Actually, let me back off and think for a moment. I should have thought before I said anything. Five and 7 I know you can do, or I think you can. Nope. 5 I know you can. Let's just stop at 5, because 7's going to be a washer, I think. 9 I think will be a disc, so that would be fine. 5 will be a disc, 9 will be a disc. 11 will be a disc, so you could do 11, 5, 9, or 11. And rather than think about it too hard, because my brain isn't willing to think, let's stop right there. We'll pick up the rest of those next time. So 5, 9, or 11 on page 461. You have a whole bunch from 7.1. We'll do that for 7.2. Any questions? All right. I think an earlier question, did someone ask about the test? I believe they did before I turned on the recorder, and I meant to come back and answer that question. The test is due when you finish it, okay? And try to get finished before we get through with chapter 7. And we're making decent progress, but chapter 7 is a long chapter. It looks like it has at least I'm going to have to go back and check the syllabus, but I think we either go through 7.5, 7.6. I don't think we do 7.7. So, you know, it'll be a few days, maybe a week, more than a week before we finish. So you have plenty of time to work on your test, but please don't put it off, because you don't want the second test coming out there while you've still got the first. So any questions before we check out for today? Okay, starting off, I'm going to stop sharing because I'm sick and tired of sharing. All right, and unless I hear any questions, we'll end the meeting for all of us. Any questions? Take care, folks. We'll see you on Wednesday, okay? Bye-bye.